Okay. Yeah, thanks, Shomo, for the introduction. And let me also thank the organizers for putting together this wonderful meeting. It's always sort of great to interact with the community working on this general topic. Let me also thank Shumilan Banerjee and Piotr Siran for their talks, because that really set up a lot of what I would be using in this particular talk. So I can sort of skip over many of the sections of the talk rather quickly. Okay, so what I'll talk about is the connection between the dynamics of local observables. That's something we are interested in. And when I say we, I mean the general community, including theorists and experimentalists, and something which I'll call Fock or Hilbert-space propagators. And the interest in this stems from the fact that these are things which actually can be calculated with a certain degree of control. This particular work that I'm going to talk about, here's the reference if you're interested, look at that. And this was sort of, almost all the work was done by Vikram Pine, who is my PhD student in the audience. So all the questions should be addressed to him. And also, I had a long-term project student who did a large part of the numerical calculations. All right, so just to set the stage, the sort of dynamical phase diagram of disordered interacting quantum many-body systems is something that has occupied our time for the last decade and a bit more. And the sort of overarching question here is that if I have such a system and I tune the disorder strength, then what happens to the phenomenology in terms of the dynamical phase diagram? So the rough understanding that has emerged is that at very weak disorder, there is an ergodic phase followed by something which looks like an anomalously slow, subdiffusive or slow dynamical regime, followed by something which can be pre-thermal. And then, of course, there is the elephant in the room, which is the many-body localization transition. We don't know whether this really drifts off to infinity, and if it doesn't, then what is the nature of this transition? And then there is the much discussed many-body localized phase. Now, of course, this looks all very nice, but because these systems are all interacting, disordered, and really far out of equilibrium, most of the quantum many-body theory that we learn in our undergrad and our graduate coursework really goes out of the window, and that's really at the root of why there is so much debate as well as so much interest in this field. So despite the existence of such a nice picture, there are lots of questions. Of course, there is the question of the existence of the MBL phase. There is the issue of what exactly is the critical disorder for the MBL transition in some of the standard models, as Piotr was hinting at in his talk. And then, of course, there are questions about the role of resonances and the possibility of this extended pre-thermal regime preceding the transition. Many of us have tried several things, but really, as you might have realized over the last week and a bit more, that there is no complete consensus on any of this. The issues are not just limited to this part of the phase diagram. There are lots of questions somewhere in this part of the phase diagram as well, which is whether this subdiffusive of slow dynamics is only transient, and it eventually gives rise to fully ergodic dynamics or not, and what is the mechanism of this? Possible slow dynamics? I mean, some of this has been attributed to rare Griffiths regions, but then there are arguments against that as well, because this also happens in quasi-periodic systems where we don't have Griffiths regions, but then the rare region effects come from initial states and so on. So there is a whole host of questions there as well. And again, there has been a lot of work in this part of the phase diagram as well, including work by our chair. So you can also ask some of the questions to him. All right. So unfortunately, I am not going to answer any of these questions here in this talk. What I'll try to do is I'll try to sort of come up with a way in which we can possibly connect some of these questions to what I'll term or what I'll call Hilbert-space propagators. And of course, calculations of those propagators is a completely different work and a sort of talk on its own right. So I'm not going to go into that, but I'll try to make a concrete connection between those two quantities. All right, so just to sort of put things on a slightly more concrete footing, this is the kind of setting we'll be interested in. So we'll typically deal with spin systems. There will be a part of the Hamiltonian, which is disordered, is made up of sigma z operators, let's say, and this favors localization. And then there is a part which gives you the quantum fluctuations and tries to delocalize the system. Now, Hamiltonians are good, but we'll actually work with flow K systems. It's not very different in some sense, because there is a part of the flow K unitary which tries to delocalize, and then there's a part of the unitary which tries to localize. And this has some practical simplifications in terms of numerical simulations and not having to worry about density of states and so on. But also it seems that possibly, again, this is something that Piotr mentioned in his talk, it seems like low-case systems are slightly easier to deal with. All right. Now, this is the sort of general setting that we are interested in. But instead of dealing directly with these complicated systems, what I'll try to do is I'll try to motivate the dynamics of the many-body state as that of a fictitious single particle on the Hilbert space graph. And I'll draw this mapping concretely. But the basic picture is that on this Hilbert space graph, each node is a basis state. You can think of it as the eigenstates or the many-body eigenstates of this Hz part of the Hamiltonian or the unitary. And then this quantum fluctuations actually gives you all possible hoppings between these many-body states. Of course, this is a very, very complicated graph. And not only is the topology of the graph quite complicated, but as Shamilan mentioned in his talk, these nodes actually have random but very strongly correlated energies. But the essential point here is that this fictitious single particle picture allows us to actually compute some quantities, I dare to say semi-analytically, and this is actually useful because if I can calculate some quantities here analytically or semi-analytically, and then connect this to some real space observables that are of interest, then it's an indirect or rather a two-step handle, but semi-analytic on the real space observables. And it's the second part of the story that I'll focus on in this talk. Okay, but before I sort of go to this picture, let me just say that when I make this analogy, then it's very tempting to declare this problem as equivalent to an Anderson localization problem on a high-dimensional graph. And there are good reasons to do that because there are features which look very similar, such as the eigenvector correlations, the scaling laws near the transition, phenomenological RGs near the transition, and so on. But then there are very good reasons to actually not make this connection because this Hilbert space graph actually encodes the underlying locality of your real space system, which is completely missing from this RRG picture. Secondly, this locality allows you to define a notion of distance on the graph, which is directly connected to your real space observables. For example, one of the notions of distance on this graph is really the Hamming distance, and that is really equal to the number of spins that are different between the two basis states. And then, of course, we have very strong correlations in the MBL phase, and in fact, in a work which is now almost 4 years old, we showed that these correlations are actually a necessary condition to stabilize the MBL phase. And this is again something that Shamilan mentioned in his talk, that if you just do the naive counting argument of connectivity versus disorder in a random regular graph, you're never going to get an MBL phase. Okay, so the question sort of can be sharpened to the dynamics or the statics on this Hilbert space graph. In how do they encode the dynamics of the local observables, and how do you make this connection concrete? And this is the question that I'll try to answer. Now, I must say that efforts have been made in this direction before also. In this paper by Giulio Biroli and Marco Tarzia, what they said was, let's throw away all the correlations, and let's just assign a random variable which is plus or minus 1 to some random regular graph, and let's just pretend that this is the configuration of some fictitious spin half degree of freedom on. But of course, the problem, then they do the dynamics on the state of this graph and sort of try to mimic some spin dynamics. But of course, this is completely contrived, and although a good first step, what we would like to do is we would like to make a concrete connection between such a picture and an actual spin chain. Okay, so let me start with the sort of basic picture that we have. So my initial state is some product state, and that can be sort of visualized as a big dot on this Hilbert space graph. And then as the state evolves, what happens is that these spins actually scramble. Different parts of the system gets entangled with each other, the autocorrelation decays. At the same time, the state actually spreads out, or the wave function of this fictitious single particle spreads out on this Hilbert space graph. So now, of course, we would like to connect these two pictures, but the reason we want to connect these two pictures is that real space correlations are often observables. Possibly we can measure them in some of these ion trap or cold atom experiments. But the problem there is that it's very difficult to develop microscopically rooted analytical theories for it, because these are interacting out of equilibrium systems. On the other hand, on this side of the bridge, you can actually develop analytical microscopic theories possibly. But of course, you cannot have a free lunch. So the price you have to pay is that this graph is very complicated. But it turns out that the locality of the underlying system actually allows us to make this connection very concrete. Now, I keep saying this connection, so let me now make it very precise. What are the two quantities that we are trying to connect? And the two quantities that we are trying to connect are basically the two simplest autocorrelation functions that you can define on either space. So in real space, it's really the spin-spin autocorrelation function. And on the Hilbert-space graph, it's just the return probability. Now here I've averaged over all the real space sites. I mean, that's almost customary. Here I have averaged over all possible initial states, okay? And the sort of main technical aim of this talk is to develop an analytic relation between this quantity and this quantity. And of course, this is something that I'm claiming at the moment that can be computed analytically even for these correlated graphs using some approximations. Okay, so before I sort of go into making the connection, let me say a few things about the return probability, which is actually quite crucial. Which is, remember that this graph actually is such that the typical or the average connectivity of the node is actually polynomially large in system size. It's typically extensive for short-ranged models. So that means, or one of the manifestations of this is that at any finite time, the autocorrelation is exponentially small in system size. This is just because at every step, the state has order L channels to leak out. So what that means is that this return probability itself is not or does not admit a well-defined thermodynamic limit. On the other hand, R of t to the power 1 by L, it actually does admit a thermodynamic limit. Okay, in fact, this is a very crucial difference between these Hilbert space graphs and trees or Bethe lattices or RRGs. In fact, in a work by Archer, where they computed this return probability for a random regular graph, you can see that if you go to larger and larger system sizes, the data is converged for longer and longer times. Whereas here, you can actually see for a non-integrable flow case spin chain that at any finite time that you take, the return probability goes down with system size. So what we actually need to do is we should not be looking at directly the infinite time limit of the return probability. What we really should be looking at is the return probability raised to the power 1 by L. Now this poses a small problem. The problem is that if I yeah, sorry about this technical issue. All right, so what we are interested in is not just the infinite time return probability, but the infinite time limit of the return probability raised to 1 by L. And because of this structure, it does not go to 0 in either phase. It actually goes to some constant. So what you expect is that the universal information of the autocorrelation decay is actually not contained in this part of the curve of R of t to the power 1 by L. It's actually contained in how it approaches its infinite time value. So the message is that it's the approach of R of t to the power 1 by L to its infinite time value that encodes universal information. So the appropriate quantity is the limit of system size going to infinity, 1 over L log of R of t over R infinity, where R infinity is really the infinite time value for a finite system. Okay, so it's this r of t to the power 1 by L, which we will try to connect to the spin-spin autocorrelation. Okay, so this connection proceeds in 2 steps. So the first step is we are going to relate the spin autocorrelation to the spread of the wave function on the Hilbert space. That obviously sort of takes in as ingredients the non-local Hilbert space propagators. And again, these are propagators of the kind that Shumilon was talking about, except I'll be doing these not in frequency domain, but in real time. And then it also naturally includes the notion of distance on the Hilbert space graph. And then we know that the total probability is always conserved on the Hilbert space. It doesn't matter what kind of other conservation laws you have in microscopic conservation laws you have in your system. Just from unitarity, we have total probability conservation on the Hilbert space graph. So we will basically use that to relate this spread to the return probability. And for that, of course, we will use the morphology of these propagators on Hilbert space. This will be a dynamical quantity. It's going to change in time. And then there'll be a certain saddle point structure. That's the technical part, which I'll go over very quickly. All right, so let's try to do this step by step. Since I have close to 20 minutes, I can do this very slowly. So first, let's define the Hamming distance. So the Hamming distance is really the number of spins which are different between 2 configurations. Now, since this S, this capital I denotes a particular configuration, this small I denotes a real space site. Similarly, capital J denotes a different configuration, and small I again denotes the same real space site. So this can, if this difference is, this difference can be 1 minus 1 or 0. So in order to compute the Hamming distance, I square it and sum up all the real space sites and divide by 4. And that actually simplifies to this particular expression. Now this is already good, because you see what has appeared is the product of the spin configuration on 2 different configurations, but on the same real space site. This is exactly what is going to appear if you try to spectrally decompose your spin-spin autocorrelation. And of course, from this, you can compute the number of states at distance r from any of these configuration. That's just L choose r, because there are L choose r ways of choosing the r spins that you want to flip. The next step is writing down this non-local Hilbert space propagator. Now, the experts will argue that this is actually not the propagator, and they would be correct, because what I have done is I have taken a mod square of the propagator, but I'll still continue to call this a propagator as an abuse of notation. So this is really just saying that if I start with some configuration J, I evolve for some time t, I ask what is the total probability on some other configuration I, and then I sum it over all those pairs which are at distance r. So really, this is the total probability of finding the state at some distance r from the initial state at a particular time t. That's just g of r comma t. And note that this g of r comma t can be actually thought of as a bona fide probability distribution on this Hamming distance space, because this g of r comma t, when summed over all r, sums up to 1. That's just conservation of probability, and this is just adding up positive numbers. So all of these numbers are positive determinant. So one can define an effective size of the wave packet on this Hilbert space graph as r times g of r comma t, and then you sum over all r. Okay, so that's just the size of the wave packet, and that's what I'm calling the spread of the wave function. And then the last step is when you take this definition, put it into the decomposition of your spin-spin autocorrelation function, you see that the spin-spin autocorrelation function is just 1 minus 2 times the size of the wave packet divided by L. That's just algebra, and that's the sort of, that's the connection between the spin-spin autocorrelation and the non-local propagator, or the size of the wave packet on the Hilbert space graph. So that's basically step 1 done. Now, the next question is, how do I actually relate this to the return probability? And as I said, for that, I really need to worry about the entire morphology of this dynamically evolving wave packet on the Hilbert space graph. So what I do for convenience is I say that this g of r comma t can be written as the number of states at some distance r times the average weight at distance r. Remember that this g of r comma t was basically the total weight at distance r. This is really the average weight at distance r. And this nr actually is, in reality it's a binomial, but I can approximate it as a Gaussian which is peaked at L by 2 and has a width which scales only a square root L. So this is actually a very, very sharply peaked function. Now, once I know this, there is another fact that I know, which is that the spin-spin autocorrelation function is necessarily less than 1 for any finite time. Okay? It's not that there is some time scale until which it sticks to 1 and then begins to decay. It really has to decay from the get-go from 1. So that means that this quantity, R of t, has to be order L at any finite time. Okay, and this is not very surprising at the end of the day, because again, you have order L channels for the state to start leaking out from the get-go. So for any finite t, R of t has to be order L. Now, if that is the case, then you can convince yourself that if this g of r comma t has to have any non-trivial behavior, then this curly f should also follow a large deviation form of this kind. It should be e to the power minus L times some other function of x comma t, where x is just r over L. So what I'm saying effectively is that the number of sites at distance r has this very sharply peaked structure, but so does this capital G, such that if you take the convolution of this, this curly f has a function which is decays like this, but has to have this large deviation form, such that if you take the convolution of these two, you get the peak of G at some non-trivial r. Okay, so now what I'll do is, just for the sake of convenience, I'll write down this function capital F into two parts. Okay, one is this g of t, and the other is this small f of t. Now, this I'm doing because, and where I enforce that this small f at x is equal to 0 is 0. This is just to take out the return probability contribution from this. This is really just a matter of notation and convenience, and there is nothing fundamental about this. Because what this allows me to do is, just write down the return probability as e to the power minus L times g of t. Okay, that's it. Now, of course, this large deviation form for f and this scaling structure I motivated using this argument, but of course there has to be there should be some evidence for this, and here is the evidence for that. So this is numerics on a Floquet spin chain. It's a non-integrable Floquet spin chain. This is one of the most commonly used models for studying these kinds of systems after the XXZ chain, and in fact Piotr showed a variant of this where, except the these parameterizations were slightly different, but roughly it's the same model that Piotr showed. And these are two different values of the parameter. Both of these are in the ergodic phase, but these are not very, very deep into the ergodic phase. These are sort of, gamma equal to 1 is the sort of maximally ergodic limit in this model, and the transition, the putative transition, is somewhere around 0.2, 0.3, and so on. So this is sort of reasonably deep in the ergodic phase, but not very deep. And you see in this, what I've done is I've taken this g of r comma t, I've divided it by n of r and g of 0 comma t. So that should really just pull out this f function. And different colors in these plots actually denote different times. And there are many different symbols, and I don't think you can see all of that because they really have collapsed on top of each other for different system sizes. So this gives you a numerical confirmation, or some credence at least, to this particular scaling form for these Hilbert-space correlations. Okay, good. So now that we know that there are these large deviation forms, then we know that everything should be controlled by a saddle point. Okay, and of course, we do the necessary checks. We make sure that there are no fluctuations beyond the saddle point which affect these results. And the answer is that basically, you can compute the saddle point equation. And as I said, the saddle point equations also should satisfy the conservation of probability, because that's basically fundamental from unitarity. And that actually gives you a relation between the return probability and this function f at the saddle point. Okay, so all we then need to do is we need to express the return probability in terms of the saddle point, and we can sort of do that. This is the final expression that you get. Again, the algebra is not very important, but the crucial point is that the approach of the return probability to its infinite time value is controlled by the saddle point and the behavior of this function at the saddle point. Okay? These are the two ingredients that go in. What about the spin autocorrelation? I mean, again, this r of t, which is just the first moment of this distribution, can be computed using the saddle point, and it just turns out to be 1 minus 2 times the saddle point. Okay, good. So now you can see that finally we want to connect this quantity and this particular quantity. Now, this x star or 1 minus 2 x star is already over here. This is nothing but C of t whole square. But there is one missing piece that I still don't know how to figure out, which is how is the saddle point or the behavior of the function at the saddle point connected to the connected to C of t. Okay, and this is the last piece of information that I need. So in order to do that, let's again go through this chain of arguments. So the first argument is that as the time goes to infinity, the non-local propagator, since I'm in the ergodic phase, as time goes to infinity, this non-local propagator should be completely uniform on the Hilbert space graph, okay, on an average, because anyway these are all averaged quantities. What that means is that as t goes to infinity, both the function f at the saddle point as well as its derivative at the saddle point should go to 0. Okay. Now, remember that the derivative of the function f at the saddle point is nothing but C of t. Now, since both of them have to go to 0, it's not unreasonable to say that the function itself goes to 0 as a power law of its derivative. Okay? Because both of them have to go to 0 at the end, and of course, this is at the moment this is just a conjecture, and I'll again show some evidence in support of this. But once I have this power, then I have a very simple relation between the approach of the return probability and the spin-spin autocorrelation. So of course, this half Ct square is the contribution from here, and this Ct to the power alpha prime is this conjecture that I am saying. Okay. So finally, we know that if this is of this kind, then at late enough times between these two terms, the term that will dominate is going to be the minimum of alpha prime and 2. So that tells me that really this is the sort of final relation, and all I need to show is some evidence in favor of this. And the evidence for this is the following. So here what I've done is I've plotted the log of the derivative of the function, derivative of this function at the saddle point, and on the y-axis I have the function at the saddle point. Okay, and both of them go to 0 together, and this is the evidence that they actually follow a power law. And of course, the point is that this data is quite noisy because the saddle points were obtained from the morphology of the Hilbert space propagators, which is sort of possibly too much post-processing compared to what is desirable ideally. But nevertheless, we get reasonably clean signatures of this power law. And you see the slope here, which is 0.1 or 0.15, is quite small compared to 2. And again, this continues to be the case throughout the ergodic phase. So that sort of tells me is that the final answer is basically this, that the approach of the return probability to its infinite time value is related to the spin-spin autocorrelation in this way. Okay. So now, what are the implications of this? So far, so good. I mean, this is basically, if you accuse me at this moment of just moving symbols and drawing connections between different quantities, I would sort of happily plead guilty because that's what we have been doing. We have basically.
Sthitadhi, one question. So during all this argument, the disorder never enters, right? So as long as
so this actually works for a clean system also.
For the clean system.
It works for a clean system.
Okay.
We have in the paper we have numerics for the clean system also.
For that, what would be the alpha? Is it 1?
It's not 1.
Okay.
It's model dependent. Okay, so but the fact that we have this almost exact relation should have some implications, and let me quickly discuss the implications. So imagine that I have a model with no conservation laws. Okay, so let's say it's a driven system, no microscopic conservation laws. In that case, you expect the spin autocorrelation to decay either as an exponential or as a stretched exponential. So I'm not going to go too much into whether it's an exponential or a stretched exponential. Again, I think Shomo is the right person to ask this question, but let's say it's of this form, beta can be equal to 1. So you take this expression, put it back here, and then it turns out that this approach of the return probability is also a stretched exponential. In fact, the stretching exponent also remains the same. The only thing that changes, only thing that gets renormalized is the effective time scale of this stretched exponential. So now why is this useful? Because once I compute the return probability semi-analytically and I really find a stretched exponential, I can actually say with confidence that the spin-spin autocorrelation does decay as a stretched exponential, and there is really it's not a transient phenomenon, as was the question posed in the beginning of the talk. Similarly, if I go to a model with conservation law, say, I have a model with U1 conservation. In that case, I expect that, at late enough times, the diffusive or the subdiffusive tails to kick in, and I expect the spin autocorrelation to decay with some anomalous exponent possibly. Okay, Z can also be 2, but it can also be anomalous. In that case, again, what happens is that the return probability or this quantity decays again as a power law. So the key point is that the approach of the return probability to its saturation actually unambiguously encodes the decay of the spin autocorrelation. So if you can compute this, which I'm claiming, and I can discuss with you later on, this actually will tell me whether the subdiffusion or the stretched exponent is a transient or it's there or not. Okay, so this is really the main result of this work. So these are the conclusions. I mean, this is really a concrete bridge between the dynamics in real space and Hilbert space. This is the sort of final answer, and these are the implications that I just went through. But what I wanted to do was I wanted to flash some future work and speculations, which might be interesting. So one thing is, of course, the analytical computation of the return probability, and this is some work in progress. I'll be happy to talk about this. That's something that I am actually much more excited about is basically, this computation of the return probability relied on something which was effectively a 2-point function on the Hilbert space. Okay, because I was looking at the probability of starting the state somewhere here and looking at the state somewhere else. That was enough to give me spin-spin autocorrelation. But that can actually be generalized to a 4-point correlation, and that gives you the entanglement structure of the states. So something that Bikram has recently calculated, and we are in the process of preparing the manuscript, is you can develop a dynamical version of this, and you can understand the possible logarithmic growth of the entanglement in the MBL phase, absolutely without appealing to the L-bit picture. So this would be a completely microscopic derivation of the logarithmic growth of entanglement in the MBL phase. So this is something that I'm quite excited about, and we'll probably put out the manuscript soon enough. And in the last, I see I have 3 more minutes. So in the last 3 minutes, let me come back to this issue of the 2-point function. And let me say that, because this concrete connection exists, this possibly can be, a starting point for understanding a generic mechanism for the glassy dynamics via the hierarchy of timescales on the Fock or Hilbert space graph. So let me spend a couple of slides on that. So this is really speculation, and ideally I should be talking about it outside this room, but since I have 2 more minutes, let me just talk about this. So the motivation comes from this 1984 paper by Eliyahu Abrams, Phil Anderson, Robert Palmer, and Dan Stein. So what they actually did here was a completely classical problem. So they say that, let's say there is a distribution of some degrees of freedom, and each of them has some time scale. So the time scale is hierarchical, and the number of degrees of freedom which have that time scale is also hierarchical. And then when you convolve these 2 kinds of functions, you basically, in principle, can get a whole host of relaxation functions. You can get power law relaxations, you can get stressed exponentials, and many, many other possibilities. There are time scales below which things can be stressed exponent and followed by a power law and so on. So all you have to do is play around with this hierarchy of time scales and the hierarchy of the number of states having that particular time scale. Okay? So that's basically the content of this paper. Now, if I go to this Hilbert space graph, then what I can do is I can write down this return probability as 1 minus the total weight on everything else. And I separate that into sums over everything that is at a particular distance. So that's the organizational principle that I'm following. And then I know that at infinite times, all of these quantities would go to, or each of these little f's would go to 1 over nh, because that's the uniform distribution on the Fock space graph. So I define this quantity, which is the deviation from uniformity, and that suggests that the approach of the return probability to its saturation can be written in this way. Now, nr really is the number of states, number of configurations at distance r. This is exactly like wn, and possibly the relaxation or the average relaxation at each of these layers of this graph happens with a time scale which itself is hierarchical. So possibly there is a hierarchy of time scales as we move down this Hilbert space graph, and it competes with, so possibly what happens is that the further down I go in this graph, the relaxation timescales increase, it gets slower and slower. At the same time, the number of states actually also increases. Okay, so there is some competition, and let me then leave you with this question: that can this be a generic mechanism for slow dynamics near the MBL transition in generic disordered systems? Okay, so that's sort of the speculation. This is something we are thinking about, and with that, let me thank you for your attention and leave you with this conclusion slide. Thank you.
So, okay. So, I'm very surprised by this result because the one side of the information content in one side of the bridge and the other side of the bridge is hugely different.
Yeah.
So, by taking log and divide it by L, you can shrink one domain, may be comparable in the size of the other, but still uniqueness is very elusive to me. I don't really understand why one has to be uniquely connected to the other in general.
I think it has to be because of the saddle point structure. So because the saddle point structure actually puts reasonably strong restrictions on the kind of results that you can get. Basically, what happens is that the return. Okay, so the spin-spin autocorrelation is definitely controlled by the saddle point, but the saddle point is also where the total weight is. So it's a bit like think about it in terms of diffusion. So if your diffusion is not completely anomalous, then you can either look at the decay of the state or you can look at the spread of the state. Both of them should give you ideally the same information.
No, I understand that, but there has to be some other assumptions, like, for example, for energy, for example, like ETH kind of stuff, for an energy range or something, you associate a bunch of states. So something like ETH or some sort of things has to be there, right? Where you associated a macroscopic energy with an exponentially many number of states or something like that.
Yeah, that's
some sort of thing must be there, right, in your assumptions?
No,
which I didn't explicitly see, but must be there.
There's no.
Suppose if you take just completely random kind of states on one side, just you don't care if it comes from some Hamiltonian or something like that. Maybe it's a pedantry, but I'm trying to understand the structure.
So I cannot take any random state, right? Because this evolution is governed, this spreading of the state is governed by the same unitary that controls the spin-spin autocorrelation.
I understand, but if this unitary is very non-local and very strange, I mean.
Sure. I mean, then you'll get something here. But similarly, in that case, the spin autocorrelation
will just relax probably.
It will also decay very quickly.
Yeah, I understand that, but the question is relaxation of a single spin versus a relaxation of a state in the Hilbert space, a hugely different information content in general.
That's why we find this interesting.
It's not a single spin, it's a correlation.
No, single spin autocorrelation, right?
Yeah, but it's still a correlation.
Yeah, it's just a single spin anyway.
Yeah, maybe we can relate, discuss it more.
No, it's a very remarkable result, that's all I'm trying to say. If
it's
correct.
Once you mentioned that this anomalous diffusion, if it happens, the decay of the height and the width is same. That's not true.
That's not true for anomalous diffusion. Now the question is, we don't actually see anomalous diffusion on the Fock space. So that's the thing. So yeah.
Okay. Yeah. Other questions? Yeah. If there is no more question, maybe let's thank Sthitadhi again for this nice talk, and we go for the break. Right.